I want to work an example for you now that involves using what's called a kinetic moment. And a kinetic moment is kind of a thing that arises out of sort of a convenience where when you do your free body diagram and you're getting ready to do your equations of motion, sometimes it's more convenient to some moments around a point that is not the center of gravity. And, when that's more convenient, it is something that you can do, but when you do it, there's another term that pops up in the resulting equation that you can't forget. It's called a kinetic moment, and you might want to check out the other video I did where I sort of explained where that term comes from. In terms of intuitively, this effect, you've experienced it before, probably, if you've ever ridden on a subway or a bus and you've tried to stand on the subway or bus without holding on to anything, and let's say it's a bus and the bus begins to start moving. If you're not holding on to anything, as that bus begins to accelerate, you feel yourself wanting to tumble in the opposite direction. And that effect is basically, if you think about summing moments around a point that would be near your feet on that bus, you can think of, unless you had this kinetic moment, there would be nothing that you could use to predict that there would be that tumbling effect that would happen. So anyway, that's just all by way of background. What we're going to do is get right into this problem now, which is kind of similar. So let's say that we have this block of wood. It says here it weighs 790 pounds. This block of wood is on the back of a truck. It gives us the coefficients of friction for 0.4 for the static coefficient of friction and 0.25 for the kinetic coefficient of friction. And the truck is going to begin accelerating. And what we're going to try to figure out is what is the smallest allowable 0 to 60 mile per hour time without this block displacing itself relative to the truck. And that can actually happen in two different ways, you can probably imagine. One of the ways is that the block of wood could slide on the bed of the truck, and the other way is that the block of wood could tumble, right? It could actually, kind of like you standing on the bus, as the bus begins to move, your feet aren't likely to slide on the floor, you're more likely to tumble over. Well, just like that, this block of wood might have a tendency in a similar way. So we're going to try to solve this, given that the block is loaded the direction that's shown on the picture and that acceleration is the direction that's shown on the picture. Once we've got that, part B here is that we're going to figure out the weight distribution that happens between the front and rear part of the block of wood when we have it at that maximum amount of acceleration we can do before the block displaces relative to the truck. So we'll figure that out. And then for the last part, we'll say, well, what if the block was actually turned around where it was kind of on the truck the opposite direction? And we'll solve that part last. Okay, I'll tell you what I'm going to do is I'm going to take the second two questions here. Tell you what, actually just the last question. I'm going to take the last question and slide it out of the way, because the first two are basically the same question, two different parts of the same question. And so we'll solve that all together, and I'll get to the last part here in a little bit. Also, preliminarily, one of the things I want to do is deal with a couple of the sort of unit conversion issues that sometimes make the problem a little bit more complicated. If we just take care of those right at the outset, that's sometimes helpful. One of those is this 60 mile per hour speed that is cited as the we're trying to figure out how much time it takes to get up to that speed. Miles per hour is not often a very convenient unit to use when we're dealing with dynamics. And so I'm going to take that miles per hour and convert it into feet per second. So let me do that down here. 60 miles per hour. And let me write that like I would where it's actually miles per hour, like this. And then what do I need to multiply by to get the miles into feet? Well, this is a conversion some of you might know, some of you might not, but it's 5,280 feet in 1 mile. Okay? And if I left this alone, I would end up in feet per hour. So I need another conversion as well. And many of you are probably familiar with 60 seconds in a minute and 60 minutes in an hour, which gives us 3,600 seconds in 1 hour. Okay, and if we calculate this out, I'll spare us doing that in the calculator, but if you actually calculate this out, it winds up giving you 88 feet per second. Okay, so that's one of sort of the preliminary calculations that I want to do on this before I even get into the main part of it, because I don't like that to interrupt the main sort of content of what we have to analyze. Okay, the second thing that let's put in here is, let's take this 790 pounds. There's another parameter we're going to eventually need here, and that is the mass. And I know pounds is weird because pounds can be both mass and force, but if you use pounds as mass, it's very often not convenient to just put it right into our equations of motion. And so I'm going to go ahead with that 790 pounds. And I'm going to think of this as pounds mass for right now. I'm going to convert that pounds mass into slugs. Well, what's the conversion for that? There are 32.2 pounds mass for each slug. So I'm going to put down here 32.2 pounds mass per slug. And that's not an exact conversion, but that's a reasonable approximation for the conversion from pounds mass to slugs. Okay, and if I do that, then this ends up giving me 24.55 slugs. Okay, so again, those are just a couple of preliminary items I wanted to get out of the way before we actually got into the meat of solving this problem. Let's get into that now. So, like with most of these problems, drawing a free body diagram is an important piece for us to do, but it's not the only important piece. It's very often helpful for us to draw both a free body diagram and a kinetic diagram. And so that's what I'm going to do right now, and I will do it for the block of wood that's in the back of the truck. Okay, so here's the block of wood. All right. And we're going to set that equal to, this is our free body diagram on the left. I'm going to set that equal to a kinetic diagram, which I'm going to put here on the right. Okay, and this is sort of the diagrams that describe the equations of motion. So the first thing we need to probably figure out is, what are the forces acting on that piece of wood? One of them's easy. One of them acts at the center of gravity. Okay, and it is just the weight of the block of wood, which because pounds is also a unit of force, I can just go ahead and call this 790 pounds, okay, as my weight that is experienced by this piece of wood. Okay, now the next thing we have to do is understand that there's probably going to be sort of a way that this force distributes between the bottom of the block of wood, and there's probably more than one way for us to really figure out what that would look like, but a reasonable enough way for us to model how the wood will really behave relative to the bed of the truck is to imagine it as if there are just two normal forces between the block of wood and the bed of the truck. So one of those might be back here, and the other one would be right here. Okay, and I need to give names to those. So let me name this one up here. I'm going to call this F because it's a force, and I'm going to call this sub R for being the right side, and I'll put another subscript on there as a normal force, little n. Okay, and maybe just a note here, maybe I'll call this point over here point R, and this point over here point L, just to kind of make that clear that those are what we're naming those 2 points. All right, over here on the left, F sub L sub N. Okay, again, that's the force on the left end, normal to the surface that it's being applied to. And then, of course, we've Because this truck is going to be accelerating, and there's going to be friction in between the surface of the wood and the surface of the bed of the truck, we could have a frictional force acting right here. And rather than do separate ones for each of these locations, what I'm going to do is just make it be one force that acts along the bottom. Again, this is a reasonable enough way for us to model how that frictional force happens between the wood and the bed of the truck. Just one tangential component of force acting along that bottom surface. Okay. Now, we've been doing this long enough that we probably are familiar by now that we're not quite done with the free body diagram, because there are some other dimensions that we might need to know about. So one of them is given right there in the figure. We actually know that there's this width that happens right here of 3 feet. So I'm going to go ahead and put in 3 feet as that width. Okay. And a lot of times when you're drawing these dimensions on your bodies like this, it's helpful for you to have in mind what equation you might end up writing. And I'll just, so I'm not hiding the ball, I look at this and say, eventually I'm probably going to find it easiest to do a sum of moments, say, about point L over here. And if that's the case, then I need to know the lengths to all of my points of interest relative to that point L, which means that I probably also want to figure out how far is it to this center of gravity to this side over here, right? Now, I won't go back and look this up, but we might remember from tables or from having calculated it in the past that for a triangle like this, the center of gravity is going to occur 2/3 of the way from a point of the triangle to the opposite side of the triangle. If it's a right triangle like this, it's going to be 2/3 of the way across, which means this is going to be 2 feet right here. And that means it's 2/3 from that side, it'd be 1/3 from the opposite side. And that actually might be helpful in case we need this length right here. This length right here is going to be 1/3 of the way from the base up to the top. And since from the base up to the top is 9 feet, 1/3 of the way from the base up to the top, because we're going from the flat to the point this time, this is going to be 3 feet. Okay. Now, that's pretty good so far. The last thing that I will add on here, because it's always a good idea to go ahead and name your directions. I'm going to call this my X direction and this my Y direction, because it's always the engineer's responsibility. Maybe not always, but it's very often an engineer's responsibility to define their coordinate system. So I'm going to go ahead and call that X and Y. All right. So that's a reasonably good free body diagram. The good news is that my kinetic diagram is very simple for this case, right? And the reason why is we are assuming that the truck is accelerating uniformly. So we can just say that acceleration that it's doing, we would expect for a truck like this driving on a level surface, it's going to just have a force, an acceleration of just A, like this, in the direction that the truck is going. Okay. Now, there is maybe one other thing that I should, maybe a couple other things that I should do here. One is, again, repeat my coordinate system. So I'll have Y and I'll have X. But then the other thing that I probably should do is indicate that this is also 3 feet. Okay, so that's my free body diagram on the left, my kinetic diagram on the right. One last thing I'll mention about the free body diagram, you will notice that I did not add any forces due to aerodynamic effects. That's because given in the problem up here, it says neglect aerodynamic forces in this analysis. It's a good thing because that would make this a good bit more complicated. One way that I could maybe, justify that, this might be a reasonable problem for us to work is right now this looks like this truck is open and you would imagine you would have aerodynamic effects. What if I change this problem though to where, let's say this was a box truck, right? And this thing actually sat inside of a box, something like this, right? Well, if this block of wood was sitting inside of a box, then it wouldn't be experiencing any of those aerodynamic effects. And so maybe let's kind of imagine the problem as if this is in a box truck instead of just out in the open. And that way the neglecting of aerodynamic effects makes more sense. Okay, let's actually get into doing our equations of motion for this body. And I want to get right into doing a sum of moments. Okay, because this is sort of where the interesting thing happens with this problem relative to some of the ones we've had in the past. When I sum these moments, summing them about point L, I mentioned earlier that that might be what I was going to do. That's a nice thing to do because it eliminates two of my variables that I don't have values for yet, f sub t and f sub L sub n. Those two variables drop out if I sum moments around point L. And so that makes that an attractive place to sum moments. That we'll notice there that when we do that, the CG is not where we're summing moments around. And once we're in a dynamic type of a problem, we always need to make note mentally if we're not summing moments around the center of gravity, because if that's the case, we're going to need to apply another term called a kinetic moment, which is sort of the big point of this problem. As far as why I'm doing it for this course. All right, let's sum these moments around point L. One of them is this 790 pounds that acts in a clockwise direction around point L. Since I've defined counterclockwise as being positive, I'm going to count this as a negative 790 pounds times 2 feet. Okay, so that's that. Clockwise tendency to rotate around point L. And then the other force that I have that would create a tendency to rotate around point L is F sub R sub N. Okay, that would tend to rotate in a counterclockwise, so I'm going to add F sub R sub N. And it acts at a length of 3 feet away from point L. Okay. And it looks to me like those are my only two forces that cause moments. And I would be tempted at this point to just say, well, I'm done. But I'm not quite. Because remember, there is this other parameter called a kinetic moment, and it's being caused by this acceleration over here on the kinetic side of the diagram. And I believe I mentioned in my other video where I talked about this, it's very often done like this, where you finish up your free body diagram side of the equation, and then imagine this acceleration over on the other side as if it was a force, but compute it and put it on the right side of the equation instead of on the left side of the equation. So here's what I mean. Acceleration times mass is force. And so I got to keep in mind what the mass is of this block. It's 24.55 slugs. Okay, and I'm going to do this real quick. Let me drop this down to another line like that. Okay, 24.55 slugs times the acceleration, okay, times 3 feet. That would be the moment. If A was a force, not an acceleration, this would be the moment that it would create. We also need to think about the direction. Would that force, if A was a force, again, I'm imagining A as a force, and I'm saying what direction would that force create a moment around point L? And it would be clockwise, which is opposite direction I'm counting as positive, and so I'm going to want to take this and count it as a negative. Again, if you want to see a justification for that, there was a previous video where I sort of showed in a more generalized case why this ends up being this way. But this is how you handle your kinetic moment term, and that is what this is down here, is called a kinetic moment. So I'll write that in here. Okay. All right. when I look at this equation, it's got two variables in it, which means I can't necessarily do anything with it just yet. So I'm going to go in and start working on my other equations that I can use for equations of motion on a 2D problem like this. So one of them is I'll sum forces in the x direction. Okay, this is relatively simple because I have F sub t, I believe, is my only force that I have acting in that x direction. I need to set that equal to the acceleration of the center of gravity of the block, which is just a, okay, times the mass. So actually I'm going to put that in there as 24.55 slugs times that acceleration a. Okay, now this gives me another equation that has two unknowns in it, F sub t and a, and that doesn't necessarily make this system any easier to solve just yet, and so I need to keep on going with my process. So the next one I'll do is I'll look at summing forces in the y direction. Okay, here I've got three different forces in the y direction. I have F sub L sub n, okay, plus F sub R sub n minus 790 pounds. All right, that looks like it takes care of all of my force components. All right, and then this needs to get set equal to, we'll go over to the kinetic diagram and see what the acceleration is in the vertical direction. And since it's just rolling horizontally on this truck where the only component of acceleration is horizontal, I can just set this equal to 0. All right, but does that help us any? Okay, here I have added, well, no, I haven't. Let's see, I've got an FLN, so I have added one more variable to my equations that I didn't have before. So I added another equation, but I also added another variable. Means I still can't quite solve it. Okay, but we're not fearful because there is one more relationship we can bring to bear on this problem. It is not an equation of motion, but we do understand how the friction side of things works, where we think of what limits how fast this truck can accelerate, which is what we're trying to find. What limits it is whether or not the block might begin to slide, and then we'll think of separately another question of it might tip also. But anyway, we know that the maximum amount of acceleration we can do is limited by how much force that's being applied right here, F sub t. Well, at the point where the sliding is just about to start, we are going to know that F sub t is going to be equal to that static coefficient of friction, because it's not sliding. Wood is not sliding relative to the truck bed yet. We're going to take that static coefficient of friction of 0.4 and multiply it by the sum of the normal forces that I have acting on the base of the block. All right, so that would be F sub L sub n plus F sub R sub n. Okay, and that gives me F sub t. All right, so F sub t is going to be equal to 0.4 times F sub L sub n plus F sub R sub n. And this, again, just to kind of make the note, this is when sliding is impending. Okay, impending is a fancy word that says it's about to happen. It's right at that threshold where it's about to happen. Well, this is nice because this F sub t, you'll notice here, exists all by itself in this equation. And so one of the things I can do is actually take this F sub t and imagine subbing it in right there. And one thing that we'll see there is that this now becomes 0.4 times F sub L sub n plus F sub R sub n. Okay? Now, look at these three equations that I have up here. f sub t is now eliminated, and I have three unknowns, f sub l sub n, f sub r sub n, and a. And I've got three equations to be able to solve it. I've decided for this particular video, I'm going to just represent to you what these answers are going to be in the interest of saving a little bit of time. So once you solve those three equations for those three variables, you end up seeing here that f sub r sub n is going to be equal to 210.667 pounds. F sub L sub n is going to be equal to 579.33 pounds. And A is going to be equal to 12.87 foot per second squared. Okay. Now, this gives us a couple of different things. Okay. Those are my answers. First thing I will note is that because we have a positive value here on the right side, right? This value right here ended up being positive. It means that there is still this contact force, this normal force happening between the truck bed and the block at point R, which means the block is not going to be tumbling. So we chose well for our first way of analyzing this problem. It means the block will slide before it begins to tumble. That will be the limiting case, is when it, whether or not it begins to slide. Okay, so that's the first thing I'll note. The next thing I'll note is that this acceleration value makes it possible for us to figure out a 0 to 60 time. And here's how that works. You might remember an equation of motion a while back that basically said that your new velocity is going to be equal to an acceleration times time plus an initial velocity. For our problem, we have 0 initial velocity because we're going 0 to 60. Okay, and now we just figured out what this constant acceleration value is going to be, 12.87 foot per second squared. Okay, which means that we can take this equation and rearrange it and say that the time that it takes to do this acceleration is going to just be equal to the velocity that we end up getting to divided by the acceleration that's being applied. And so what we'll do is we'll put in that 88 feet per second as the velocity we're trying to get to, and we'll divide it by the 12.87 foot per second squared. Okay, which if you punch that into a calculator, what you will end up getting is 6.838 seconds. Okay, and so that is, assuming the truck's got the horsepower and everything to make this thing accelerate as much as you want it to. If the only thing that's limiting how much you can accelerate is whether or not the block will be caused to move in the bed of the truck, that would be our minimum, or the minimum 0 to 60 time that we could achieve with this truck, with the block in the back of it. Okay, now part B. Okay, because I think I had part B also built into this same question. It wanted to know what's the weight distribution, right? Report the right, left, or front, rear weight distribution. That basically just refers to how much of the force of the weight of this body is being applied to the rear versus how much is being applied to the front. So let's just do that real quick in a small little table. Okay, so with acceleration, what we're going to see here is that on the left end, so let's do with acceleration on the left versus on the right. Okay, what we'll see on the left is that we've got 579.33 pounds. And on the right, we've got 210.667 pounds. Okay. And an interesting question would be, and this is what it's getting at, compare it with the distribution you would have if the truck wasn't accelerating. So let's say if we don't have any acceleration, okay, if we're without any acceleration, what would this distribution of weight be between the front and the rear of the block? And not to, belabor this point a whole lot, we could do a sum of moments just as a static problem around the left end, let's say, and figure out what these weights would be. But given the fact that the center of gravity is 2/3 of the way across, what that means is that 2/3 of the weight is going to be carried on the right side and 1/3 of the weight is going to be carried on the left side. So we can quickly punch those into our calculator, and what we'll see is that that would put 526.67 pounds being supported by the right side versus 263.33 pounds being supported by the left side. One of the reasons I wanted to do this is I just wanted to illustrate here quickly that there will be this shift of how much weight is felt in the front side versus the back side. A good analogy for this might be when you're standing on the bus and the bus begins to accelerate very quickly. What you tend to do as a human being to compensate for that is you apply more weight to the back side. So if you're standing facing forward, you would put more weight in your heels to try to lean yourself forward, and that's how you will try to keep from tipping over. This is a similar kind of thing that happens. You're putting more weight to the rear of the block in order to be able to do that acceleration. And so with the acceleration, that new distribution is going to have, it's almost reversed, right? You're going to have more of that weight to the rear. And that is being caused, the only reason that happens is because of that kinetic moment term that happens right there. That's what causes that shift in the weight distribution. Okay, so we've done parts A and B of this problem. Part C asks an interesting question. It says, what if the block was loaded the other direction? Okay, and I tell you what I would like to do on this. I'm going to take this question and I'm actually going to slide it up higher so we can still have a picture of the main problem in front of us while we work this problem. So let me do a little bit of sliding around here. All right, so what if the block was loaded the other direction? Okay, well, let's start by doing our Freebody diagram and kinetic diagram again. So here's my Freebody diagram, and I'm going to equate that to a kinetic diagram like this. And as we look at this, everything is pretty similar to the last set of Freebody diagrams we did. We'll still have our 790 pounds here. I can still name this FRN. I can still name this FLN. Okay. I'll still want to have my some of my dimensions shown here, so I'll say that's 3 feet. Okay. One thing that I also need to put my tangential component of force right here, F sub t, because that's what's being caused by the friction between the wood and the bed. Okay. What I'll notice here is that this is, I'll do it down here, I have a 1 foot spacing right there. Okay. And to complete it out, I'll say that's X. I'll just say this is Y right here. Okay. I can do the same thing over here. This is X and Y. And I need to show what's going on with the center of gravity of this body. So that's an acceleration that happens right here. And to be complete, I want to also say that this is going to be 3 feet. All right. So I think I've almost, if not everything, I've got almost everything that I did on my old Freebody diagrams that I had before. Slide this up a bit so we can see them all at the same time. Okay. They're almost exactly the same. What is the one difference? The one difference that's going to change what happens in our problem is that the horizontal spacing now is 1 foot as opposed to being 2 feet in this diagram. Everything else that's substantive about the two problems ends up being the same. Okay? And because of that, what I'm going to do is I am going to actually take all of these equations so that I don't have to write them all again. Take all of these and copy them. One of the nice things about working in a kind of an electronic environment like this is I can just take all of that stuff and literally just copy it. Okay? And once I've copied it, I want to make sure I change the one thing that should have changed, and that is that this 790 pounds, the line of action of that is no longer at 2 feet right here. It's now just 1 foot. But the rest of it stays the same. It's the only thing that changed by us flipping that block the other direction. Okay? But that does change the outcome of all of these answers. And I'll say again, this ends up being reducible down to a 3-equation, 3 unknown system by doing that substitution of f sub t. And once you do that, you will find that f sub r sub n is going to be equal to negative 52.667 pounds. F sub L sub n is going to be equal to 842.667 pounds. And A, not surprisingly actually, but A stays the same at 12.87. The reason I say it's not surprising, that's in foot per second squared. The reason I say that's not surprising is that there really isn't fundamentally something that changed in terms of how much force we have available to accelerate this block. F sub t is still limited by the amount of friction, and FLN and FRN are always going to sum to that 790 pounds based on the y equation that I have right here. So it's not surprising that I can get the same amount of acceleration as I did on the previous problem, right? Here's what is different though. Okay, this is an important point to make. This FRN right here turns out negative. If this block really is just resting in the bed of this truck, this can't happen. Okay? The only way this could happen is if the block was like glued down or something to where you could put essentially a tensile force between the bed of the truck and the block of wood. That doesn't happen just by there being contact. So, since this can't happen, what does that mean? All right? What this means is that the block will not slide first. Okay? If you actually take this block up to the acceleration rate that would be necessary in order to make the block slide, before that happens, the value of FRN has gone to 0 at some point, and when it does, as soon as that FRN goes a little bit past 0, kind of into the negative zone, what will happen is that block of wood will instead begin to tumble backward. Okay, so I'll just say here, it will tip. before it slides. All right, well, shucks, that makes this analysis not actually useful now. We need another analysis to tell us how fast can we accelerate this thing without causing there to be some sort of motion of the wood relative to the bed of the truck. And in this case, tipping happens before sliding. So what we need to do is change our free body diagrams just a little bit. Okay, and because I'm not going to change them a lot, what I'm going to do is copy what I've currently got, paste them down here. Okay. And then change the one thing that matters, right? So this is still F sub t. The one thing that I need to change, once I've assumed that the thing will begin to tip, what changes is FRN goes away. Because as soon as it begins to tip, there's no longer any force that's going to happen toward the right side of the distribution of force between the wood and the bed of the truck. And once that value goes away, we end up writing actually a simpler equation for our very first M sub L equation that we have up here. So I'm going to rewrite that equation. This is now assuming tipping. Okay. When I rewrite that equation, I'll sum moments around point L, counterclockwise being positive, and I'll have this, clockwise, so negative 790 pounds times 1 foot. Okay. And with that 790 pounds times 1 foot, I'll set that equal to the kinetic moment term that comes from the opposite side. And that doesn't change. It's still going to be minus 24.55 slugs times A. I'm going to give myself a little more room here. Times 3 feet. Okay. Now, what you'll notice about this equation, we now have only one thing we don't know in this equation. And so from this equation, we can solve for A. And A ends up being 10.726 feet per second squared. Okay? And that is different than what we had before. We cannot accelerate as fast as we thought or as we could when the block was the other way, because before we could accelerate all the way up to the point where the block began to slide. Now it's going to tip first before it slides, and so we have to slow it down just a little bit, that rate of acceleration. Okay? Well, now, based on this acceleration rate, we should be able to do something similar to what we did before and figure out a 0 to 60 time. We do that by taking the 60 miles an hour, which is going to be 88 feet per second, and dividing it now by the 10.726 foot per second squared acceleration value we just found. And when we compute that, it ends up telling us that we're going to need 8.204 seconds in order to do that 0 to 60 time without displacing the block. Okay, so just to recap, what we've accomplished here is we've, first of all, shown an example that uses a kinetic moment term, and that kinetic moment term arises because we are summing moments on our free body diagram about a point that is not the center of gravity. So we need this other term for a kinetic moment term. Okay, and we've figured out that it matters what direction we load a triangular block like this, because in one case, with the case that's shown, the first thing that happens as the truck begins to accelerate is that the wood will slide backwards, just sliding along the base, the bed of the truck. And if we were to flip that block around, it will no longer slide, it will instead tip backwards. And that happened just due to the fact that our CG is now shifted relative to the points where we can imagine the reactions would occur on the edges of the wood. We also figured out for the case before, the case shown here, we also figured out that there was a change that happened in the weight distribution from the front to the rear because of the acceleration that the block was experiencing. I hope this has been a helpful video, and hope you'll catch me on the next one. So thanks for watching.